Hello everyone. Thank you for joining today's webinar. I'm Jeong from Virtual Lab. I'm responsible for the Material Square team. Here is the today webinar contents. First, briefly introduce to webinar topic and the importance of structure modeling in the DFT simulation. So I will then introduce to the modeling tools, Material Square. Finally, I will demonstrate how to model structure, surface structure and heterostructure using the Material Square modeling tools. If you have any question during the webinar, feel free to write them using Q&A channel. Okay, so many simulation beginners say that the modeling structure is very difficult. So I know modeling structure was my biggest problem when I started simulation. So Material Square provides various modeling tools to help users build the structure easily. However, many users find it difficult to know all the MatSQ features available to them. So in today's webinar, we will have a hands-on session, so you can follow along around how to model structure step by step in the Material Square. By the end, I hope you will feel for the easily and confidently using the Material Square modeling tools. The structure modeling is the one of important and most challenging part of the DFT simulation. If the initial structure is incorrect, the optimization process might lead to an unfavorable structure, and the structure may not reach the most stable state and get stuck at the local minimum. If the initial structure is well prepared, well defined, you will get fast convergence, which in turn reduced computation time, the computation resource, and the well-designed structure also the reduced computational error in the DFT calculation. So I will introduce some cases, the bad modeling case. Pre-continuous mistake made when creating surface structure is to set the vacuum layer too thin. If the vacuum is too small, the system can behave like the interface rather than the isolated surface system. This structure looks in the like this well-defined vacuum region in here. However, we repeat the construction along the direction in the periodic boundary condition. Then if the vacuum is insufficient in here. So in this layer, in the interactor is the top and the bottom layer, affecting the adsorption energy and charge distribution of the surface and the surface properties in this structure. When the modeling surface, already check the probability and make sure there's enough vacuum region. Maybe I recommend this 50 angstrom and rest in the structure. Periodic boundary conditions apply also the XY plane. So for example, you made the water and the oxygen molecule far apart. Maybe they do not the interaction with each other. Maybe about 12 angstrom and each other distance, which might look fine in the single unit cell. However, when the periodic boundary condition is applied in this system, they may be closer than the expected about and here the 4.6 angstrom. So very small than this your expected distance. Distance is resulting in the intended interaction between the molecules. So when the studying adsorption interpation reaction, it is important to check of the periodic boundary condition, as interaction can affect the final result. When modeling heterostructure, a common mistake is ignore the lattice mismatch. If you simply merge two structures without adjusting their lattice parameter, they may look fine in the unit cell. However, when you apply the periodic boundary condition, you can see the distal structure is like this, and the atomic misalignment. When modeling slab structure or interface structure, a periodic boundary condition is applied by default. So there is the high risk using a wrong model if the repeat structure is not fully considered. So in heterostructure modeling, it is essential to consider supercell size and the strain adjustment to minimize the lattice mismatch. Okay, before we start modeling, it is the brief go over some key concept of crystal structure. Crystal structure consists of basis and lattice. There are two types of crystal structure representation, maybe the primitive cell or the conventional cell. The primitive cell is the smallest repeating unit that can generate the entire crystal by the periodic translation. It contains the maybe minimum number of atoms required to define the structure. And in here, in the case of a base-centered cubic, the FCC system of primitive cell, it has a non-orthogonal lattice constant in like this. Lattice vector A1, A2, or A3 vectors. It contains only one basis atoms in here. However, the conventional cell show the crystal structures more clearly, maybe in the cubic system. It contains more atoms than primitive cell, but help in the understanding of the overall system and the atomic arrangement of the crystal structure. For example, FCC crystal structure in the conventional cell. A conventional cell is maintained a cubic system like this. The cell vector parameter is the A1, A2, A3 like this. It's very simple with the four basis atoms. We need the way mathematically define the specific pace and orientation in the crystal structure. The notation used for this is the mirror index. The mirror index is the indicator of the specific plane or the paces in the direction, like that, such as a vector of the crystal lattice, and it is written is the form the H, K, L, like a is plane and direction. A plane is written as like this. 100, 11011, or the 110 or 001. It is referred to the specific plane in the crystal structure. However, in direction, it's written by something like this, referred to the specific crystal orientation or crystal vector. Okay. I will introduce to you the MatSQ modeling tool, and which allow you apply this created structure, surface structure. MatSQ provide modeling tools that create a variety of structure. There's a structure builder is for creating crystal system, and the molecule builder is for creating the molecule or the polymer system. Molecule builder is referred to as converting the molecule or polymer structures from the 2D to the 3D structure. Since we are doing the crystal structure modeling in tutorial today, we'll focus on structure builder and exploring their features. When you log in the MatSQ and click on the new work, the structure builder appeared in your system. There are three main tabs in the structure builder, and one is the modeling, cell, and atoms tabs. In this webinar, I will introduce the feature of these tabs one by one. The modeling tabs provide the ability of the import structure or create your own structure. You can import crystal structure database from the material project. It is the open database, or you can upload your own structure file. You can also import the structure from a previous simulation job or your job and add a structure from the other modules on the current work page. Also, you can also create a structure by entering the parameter of crystal structure or by draw the molecular structure. The cell tab is provide ability to make various modification of crystal structure or the surface structure. You can resize the lattice or compress or stretch the structure, create a supercell to expand the structure to multiple repeats, add a vacuum region to create a surface model, and apply the mirror index to create a surface structure. It is also provides the ability to merge two structure and convert between the primitive cell and the conventional cell. And the atom tab provides the ability to add the position in individual atoms or molecule. You can add new atoms or molecule to the structure or the randomize the placement of atoms or molecule in created cell using the fill function. And selected atom can be moved or rotate and substitution is them with the other atoms. This function is a summary of each these features can be found in the MatSQ documentation page. Now it's time to create a structure. Among the various surface structure, we will create a row index surface called bulk. The workflow for the creating surface structure is a 6-step. First, load to the primitive cell structure of gold and convert it to the conventional cell from the primitive cell. Set the orientation of the bulk structure by selecting by mirror index and repeat the cell using the clone function to increase the number of layers for the surface structure and add the vacuum region to create a surface. And finally, convert it to primitive cell to make it a unit cell. Okay, now let's create a surface structure using the MatSQ workflow. Maybe MatSQ login, go to the MatSQ homepage, www.materialsquare.com. And then the login. Then I will move to the work page to add the new work. First, create work in the MatSQ to open the structure builder. And then click the database button in the modeling tab. Choose the selected MPID. I entered this MPID in the 18.1 for the cold bulk structure and click the search button. Okay, select the desired structure from the list in here and click and add it. You can see the cold bulk with the primitive cell. Now let's convert the primitive cell to the conventional cell. And close the window. I go move to the cell tab. And then you can see the conventional icon. I'll click the conventional button. And you can see the conventional cell called surface, called bulk structure. Okay, here we can use mirror index to create a space. However, it is important to note that we need to find the lattice constant of gold for the calculation. Depending on the input parameter before making the surface modeling. That means we need to run the VC relax calculation first and then to find the lattice constant and then use the mirror index. However, since our goal in this webinar is to only using the modeling tool, so we will just skip in this step. Also, we will to make the mirror index. Click the in cell clip button. It button is to convert to the bulk structure to desired mirror index orientation. Enter the mirror index in here and value the crystal pace, then you will form the surface or the surface structure direction of these spaces. If you want to create this 100 pace surface, you can enter the 100 for the HKL. If you want to create it 110 surfaces, you can enter the 110. However, I'm going to create this 111 faces, 111 surfaces for the gold. So I will enter is 111. And then after enter the mirror index, enter the so in here, maybe 15 for the max C value. This value is assigned to the root per different structure. Maybe when running the mirror index transformation, considering symmetry. So if you don't enter in this value, only the smallest C value will come out. So make it a little larger just in the case. Click the apply button. We will generate the several lists for the symmetry of one mirror index. You can select the common direction vector with the angles 19, 19, and 16 here. Okay, you can see the one-on-one mirror index in the bulk gold structure like this. Then you can use the clone function in here to create the surface by increasing layer of gold surface layer in the C direction. However, suppose gold one-on-one surface and 6 layers common layer in the calculation. So since we have already created 6 layer in the current structure, so we will not increase the number of layer. Next step is to add vacuum. Add the vacuum region to create the surface. When setting the vacuum layer, it is important to make enough vacuum region to the period boundary condition. And so click in the vacuum button. It is usually recommended to have vacuum region at least 15 or 20 angstrom. So in this session, I will only just add the 15 angstrom to vacuum region. So I entered in 15 for the plus C direction and apply. And you can see the gold one-on-one surface in your visualization. Okay. Finally, we convert the primitive cell to create the most basic surface system. For gold one-on-one surface, based on the primitive cell, there are shoot one atoms on the one single layer. However, the current structure in this structure is the maybe 2 by 2 supercell size with the 4 atoms in 1, 2, 3, 4 atoms on the single layer. So we could use these structures. It is possible. However, we will convert it in the primitive cell because to see the lattice parameter of the surface structure. To do this, like this, click the primitive. Okay. You can see the primitive cell based called one-on-one surface structure. Do you finish that? Okay, if you have not, I will give it about 1 minute to finish. Maybe if you finish it is making the one called the one-on-one surface, you can try to create different surface structures by applying the different mirror index value. Okay, let's start modeling the heterostructure. Now, let's talk about creating heterostructure using the two different structure. The most important things, to check lattice constant of each structure. Sorry. Okay. If the cell parameter of two structures may very different, you must apply the strain to one of them to make them match. But if the difference is too big, it will be caused the much deformation on the side structure. So that means the change in the original properties. Therefore, so before merging two structure, you must calculate the lattice mismatch and determine the special size that minimize the strain effect. The lattice mismatch equation in like this. The lattice mismatch of less than the 3% is very good structure. But 5% is or less is the considerable acceptable in the DFT simulation. In this session, we will be modeling heterostructure using graphene and gold one-on-one surface. So let's start by calculating the lattice mismatch of structure. The lattice constant of gold bulk is provided by Materials Project is in 4.17 angstrom. So the lattice constant of the gold one-on-one surface is 2.95 angstrom. That means that if you combine the graphene and gold one-on-one surface in the 1-to-1 ratio, the gold one-on-one surface will have a strain of maybe 16.4 percentage. This value is very, very large, also making it difficult to form stable heterostructure. So we need to find the way to reduce the strain effect by combining the n by n supercell of gold one-on-one with the n by n supercells of graphene sheet. So now let's compare to the cell parameter of different supercell size in gold one-on-one surface and graphene. Maybe a good combination is graphene is 5 cell supercell and the gold one-on-one is 4 supercell. It calculates the strain effect on the gold one-on-one surface is in the maybe in here. In this combination it is about the 4.5%. Another candidate combination is the graphene 6% and gold one-on-one is 5%. In this case, the strain in the gold one-on-one surface is very small, as only 0.4%. Also, computationally, the second combination is the smallest strain is the most ideal structure to use in the calculation. However, the second combination is the supercell size increase, the number of items also increases, so increase the computational cost. So in heterostructure modeling, the choice of supercell size should be based on the both computational cost and physical properties of structure. Let's consider the heterostructure of graphene and the MoS₂ layer. The lattice constant of the graphene is the 2.46 angstrom, while the MoS₂ lattice constant is the 3.19 angstrom. That result in the lattice mismatch in the 22.7%. It is also very large, so we need to define the size of the supercell to minimization is the parameter difference. So the first considerable combination is the graphene 454 supercell and the MoS₂, the 3x3 supercell. This combination lattice mismatch is the only just 3.0 percentage. Another combination is the graphene 505 supercell and MoS₂ 454 supercell. In this case, the strain of the MoS₂ is the 3.4 percentage, which is not as much different as with the previous case. So in this case, in the strain of MoS₂ is only 3.2 in structure, first structure. So using the smaller cell is a very variable for the TFT calculation. So in here, there is the one important thing to remember when working out the size of the cell for your calculation, your structure. As I said before, the value is the lattice constant is very just example from the materials project database. They are the based on the data provided by materials project. So we should always use your own calculation lattice constant to make decision of the supercell size. For your own research, you should always calculate of the lattice constant first, and then determine the supercell size based on your software, your potential file, and your input parameter. Okay, now let's build on this concept to model the actual heterostructure. Heterostructure modeling workflow in here. First, import the structure like this called one-on-one graphene and MoS structure, and then create the supercell. And then we will change the cell parameter of the structure to which we want to apply the strain. And then we merge it to structure together, and then finally adjust the move to the interlayer distance. It's okay. We will move to material scale to using the material scale tool. Yes. First, we will create heterostructure graphene on top on gold one-on-one surface. So we will use the optimal supercell size and the 454 gold one-on-one surface and the 555 graphene unit cell. So that we found in the previous lattice mismatch calculation. So we start adding the new structure builders to create modeling and structure builder. And first, load the called one-on-one structure you created in the previous step like this. So in the modeling tab and module, click the module button and okay, sidebar you can decide by select the structure builder within the called one-on-one surface primitive cell and load it like this. And then use the clone function to move to cell to create the clone. Create a structure of the 454 supercell. Then use the 4 and apply. Okay, you can see the gold 111 454 supercell size. Next, we will create graphene structure. We will add this structure in the same structure builder. So we add the structure builder, structure list. Click the list icon in here, and then plus icon. In this, copy the same structure like this. And then we search it and add graphite structure using database. So go to the modeling and the database. So using the MPID 48. Click the search button and the list is click to add. You can see the graphite structure in this here. Click this pin icon. Yes, this icon to move to the graphite structure list all. And then in delete is copied a called one-on-one surface is deleted. Now let's move to one layer from the graphite structure to create graphene layer. Click in this finger icon and click rectangular and select the method single. And then drag in here visualizer and select the one layer graphene. And then the selected atoms will be marked with the blue border like this. So press here. Press del keys on your keyboard on deleting the selected layer. And click on the ESC button in your keyboard. Go to the cell tab and clone. And create the 5 by 5 supercell of graphene. You enter the 5 and click apply. You can see the graphene 5 supercell size. Now we will merge two in the structures called one-on-one surface and the graphene structure. Before we merging the two structure, we need to make sure that the cell parameter is the base structure and attached structure is the same. It's important to get right down to the maybe decimal point. So we will modify both structures. First, check cell parameters base structures graphene. We should graphene is base structure because it is more strain sensitive than gold surface. So go to the modeling tab and click edit. Change the lattice parameter. And then you can see the lattice parameters graphene lattice. We set the A and B values to unity. So we are deleting here, maybe string like this, and copy and paste in the B section. Okay, and then we are the fractional, change the fractional in the upright. If cell keeps cell size, okay. The fractional coordinate system determines the position in the of the items based on the cell vectors. So we should use the fractional system when the changing of the cell parameter. The change the lattice constant lattice parameter is called one-on-one surface like the graphene lattice constant. So we will copy and graphene lattice constant, Control C, and then we move to the gold surface and click the edit. Paste in A, B inserted in this value and change the fractional to apply. Maybe you can see the change the lattice constant in gold one-on-one surface, like same as the graphene lattice constant. Like gold one-on-one in graphene lattice. Lattice parameter is set the same, the both structure, graphene and gold structure. There's another thing to note before merging. Atoms, the boundary in here, maybe like this in here, in these atoms. And so atoms on boundaries sometimes don't merge, so move to the them very slightly so that there are no atoms in the boundary. So select mode rectangular. So select all atoms called or the graphene is slightly move to button. So atoms move pointed 0 very slightly apply. And then another is the graphene, the same. The select mode into all the atoms of graphene sheet. The move the pointed 1 and very slightly to move. And now we will merge graphene and gold one-on-one surface and create the heterostructure. Okay, let's see. Cell, merge, create. And base structure is the, in structure list in here, base structure is the graphene. So structure 1, so select structure 1. And attachment structure is called, so structure builder, in name is structure builder. And we are the order to the origin base attachment. No, we are base structure graphene, so it's a base structure upper to the attached structure. So we are selected order, so origin, attached, base structure, and apply. And in here, and it's heterostructure. Now it's been created, so merged to structure like this. In here. However, since we already original structures with the vacuum region is graphene and gold one-on-one surface, so there is too much distance between the structure. So I will move to graphene close to the gold one-on-one surface. So select rectangular, drag to the selected graphene layer, and move to the gold one-on-one surface closer. So we can two methods. One is using the keyboard or arrow button in like this. However, second is the atoms and move button. So we are the move to the G direction is out downward to the cold 1, 1 surface. So minus. Clean button is at the tab. So enter G like this. Move to sorry. Yeah. Okay. We are the make the heterostructure graphene on the cold 1, 1 surface like this. Maybe this structure lattice mismatch is 4.5%. The cold 1, 1 apply the strain effect. The using MoS₂ and graphene lattice constant create heterostructure in graphene MoS₂ in the same way. The edit modeling the structure builder and creating unit cell for the database and MPID 84 and this and then it's select mode. Yeah, rectangular select mode and then delete in your keyboard and press yes button and then clone. Maybe graphene layer is 4. First is 4 apply and you make the graphene lattice. And then next is the pros. You can click the structure list and add the structure list. And then modeling and using the database. The MoS₂ is the 2815. In here, click like this. The graphene is MoS₂ structure is the hexagonal cell, but MoS₂ from the materials project cell is the different angle for the gamma. So maybe graphene system is the maybe 120 angle degrees. But MoS₂ is from the materials project is the 60. So we will change it in the gamma angles. So edit, change the lattice parameter, and in here 120 degrees, right? Okay, like this. Okay, in here. And then the press the pin icon. So I deleted this other structure. And then click the finger icon and rectangular, drag and the post layer and delete it in your keyboard. And ESS button. And then increase the supercell size cell in clone 3, 3, 1, right? You can make the supercell size MoS₂ support the 3 by 3 supercell, and then graphene is 4 by 4 supercell. Move them very slightly so that there are no atoms on the boundary. So select mode in here, rectangular. All atoms of the graphene and atoms. Sorry, to move. 0.1, 0.1. There's no atoms on the boundary in here. And then MoS₂ structure the same. select all atoms, and then move. Right. And there are no atoms in the boundary. Okay, now let's create a graphene and MoS₂ heterostructure. Then edit in lattice constant or the MoS₂, same the graphene lattice. Here. We'll check the lattice constant of graphene, modeling, or click the edit. Copy it in the A lattice constant, same to B, and move to the fractional, change the fractional, and apply. And copy in the graphene lattice of A, change the MoS₂ lattice constant. Is A, B, fractional, apply. Okay, the MoS₂ supercell structure lattice constant is same to the graphene lattice constant, like this. We're using merge in the combined the two structure. Then, okay, I will see the structure list. Structure 0 is the graphene, structure 1 is MoS₂. Merge, base structure is graphene, attached structure MoS₂. Set origin and base attachment. Apply. You can see in this structure. This structure is a so long distance between the two structure. So I will move to the MoS₂. So select rectangular, method is single, and drag or selected all MoS₂ atoms. Atoms, move, and 0, 0, -2, and here. And this compared to the modeling the graphene and MoS₂ heterostructure like this. I can check it is okay or say the clone. It might be 2. Yes, periodic boundary condition is okay, and the structure is okay. Okay. This concludes today's webinar. So thank you, Joanna. Thank you.